Want to know one secret? You don't need to memorize formulas for areas and volume. Most of us have spent our childhood in the school trying to cram and remember the formulas inside our head, but you don't need to do that anymore. Whether you are a student or doing a DIY project at home, you won't try to remember formula. You'll be visualizing them instantly. So without wasting much time, let's dive in. Let's start with the simplest shape, a square. Now I want you to forget the formula and visualize an empty frame, an empty square. And on this empty square, if you move one of the line, let's say the left line, from left to right, and as the line moves, it fills up the empty space in the square. The line moves from left to right and fills up the entire square. Or you can visualize a paintbrush of width A, moving from one end of the square to the another end of the square, filling up the entire area of the square. So, line A, moving the distance A, makes up the area of square, which is A times A, or A square. So you saw how we converted the motion of one edge of the line to an area. So if this visualization clicked for you, then stay connected, because we are going to use the same simple trick for some of the complex shape, but the visualization would be as simple as square. Let's move ahead. Same way with rectangle, the visualization is very similar. Here the sides are slightly different in measurement. So let's say the width A slides across a distance B, A times B, that's the area of rectangle. Same visualization with different dimensions, A times B, that's the area of a rectangle. Now let's move on to our next shape, a triangle. Now things starts getting a little tricky with the triangles. Whether it is obtuse, acute, or a right angle, to make it simpler on our brains, what we'll do, we'll flip the triangles until the longest side of the triangle rests on the ground. Now drop a line from the top of the triangle to the bottom. Boom! This is your height. And if you look closely, our triangle fits perfectly inside a rectangle of height h and width b, where b is same as the base of your triangle and h is same as the height of your triangle. So your triangle is fitting inside a rectangle of dimension b times h. Look closer at the empty space in the rectangle. Those extra pieces are actually an exact replica of your triangle. So your rectangle is actually twice the area of your triangle. Since the area of the rectangle was b times h, the area of triangle is half into base into height. Still think you need to memorize formula, or is the visualization taking over you? Let's move on to more shapes. The secret to all other shapes with straight lines, they all are a group of triangles and rectangles in disguise. For example, a parallelogram, you can easily convert it into a rectangle. A hexagon, it's nothing but a group of 6 triangles. Similarly, if you move higher to octagon or a decagon, you will see that the shape smooths out gradually and the area gets closer to circle, pi r square, and the perimeter of the shape gets closer to circumference, 2 pi r. But wait, I promise that we won't be memorizing the formulas. So let's see how to visualize circles that are without straight lines. What's the best way to visualize areas for curved shapes like circle? Now before we visualize circles, I need to introduce you to a constant which is as mysterious as the universe itself. I'm talking about pi. And I want you to meet pi. To meet pi, what I want all of you to do is take a paper circle of 1 inch in diameter, cut it from one end, lay it flat and measure its length, its perimeter. You'll find that it's exactly 3.14 inch. That's the finest we can measure using a circle. You will find that it is exactly 3.14 inch, which is pi. And it's not just 1 inch circle. You can take any circle, be it 10 inch, 12 inch, 5 inch, 6 inch, whatever you want, any random size of a circle. Take it, cut it, lay it flat. When you measure the length of the circle, divide it by the diameter of the circle, you'll see that it always comes to 3.14. That's pi. And circle is not the only place where you will find pi. You'll find pi in the probability of a coin toss. You will find pi in the helix of a DNA. You'll find pi in a sinusoidal wave. Pi is omnipresent. It's present everywhere. The reason why I introduced you to pi is because I wanted you to know that the perimeter of a circle is 2 pi r. I know I told you we won't be remembering formulas, but pi is such a mysterious number. There was no other easier way for me to introduce pi to you or the circumference of a circle to you. But by doing this paper cutting exercise by ourselves, we'll be able to see it and remember it. That's the easiest we can do. Now, since we know pi, let's go and visualize the area of a circle. Now that we have met pi, let's use it to visualize the area of a circle. Let's take a circle, cut it open and lay it flat. It will make a line of length 2 pi r. Now, on this line of length 2 pi r, if I was to move radius r from one end to another, it will form a rectangle. It will paint a rectangle. The area of this rectangle would be the length of circle 2 pi r multiplied by the radius r, which is 2 pi r square. That's what the area would be if it was a rectangle. Now look carefully what happens in the circle. When the radius r is rotating and painting the area of a circle, you will see that only one end of this radius is actually moving. The other end is stationary, it's not moving at all. So out of the two ends of the radius, only one is moving and the second is not. Now, since only one out of the two ends of the radius is moving, the area that the radius paints in this case, coincidentally, is half the area that it would have swept if both the ends were moving. So the full area was 2 pi r square. Since only one out of two ends is moving, coincidentally, the area it sweeps is exactly half, which is half of 2 pi r square, which becomes pi r square. So that was the visualization of area of a circle. Now that we have calculated areas of 2D shapes, let's step into the three-dimensional world. Let's start with areas of 3D shape. We'll start with cylinder first. What happens in a cylinder? The circumference of the circle, which is 2 pi r, is moving across the height h. So the area that this circumference paints when it's moving the height h is 2 pi r times h, 2 pi r h. That's the area of the curved surface of the cylinder. If you want to add the area of the top and bottom circles, all you have to do is add area of two circles, which is pi r square. So 2 times pi r square plus 2 pi r h. That's the surface area of a cylinder. Similarly, on a cone, you will see the length L is rotating across a circle at the bottom, 2 pi r. So it is 2 pi r L, but remember, only one side is moving and the second is stationary. So in this case, again, the area would be half, right? So 2 pi r into L by 2, which is pi r L. That's the area of a cone. But if you want to add the area of the circle at the bottom of the cone, then you can add pi r square to this, and that becomes the area of the cone. Now that we have visualized areas, let's switch on to volumes. Visualization of volume is very similar to area. The only difference is now we are trying to visualize in a 3-dimension. Now the depth perception comes in. So instead of curves or lines moving and sweeping across planes, we have an area which is moving across a line and making a solid object. Let's start with the very first basic object, cube, which is the simplest, which will tell you why the visualization is very similar. So when a square of area L square moves across a plane of L, it's building an object, it's building a cube of volume L cube. So you see it's very similar to area, only thing is there's a depth perception here which makes it volume. Area L square moving across length L makes a volume of L cube. The volume of cuboid is very similar, it's rectangular, so all three sides could be different. So if a cuboid of within one of the face having an area L into B, when it moves across a line H, the volume of cuboid becomes length into breadth into height, L into B into H. That's how the volume of a cuboid is measured. So now you see how we apply the same principle of visualization of area to visualization of volume. Now that we have seen basic shapes like a cube and a cuboid, let's switch on to some of the more complex shapes and look at how to visualize their volume. Similarly, the volume of a cylinder is again area in motion, area of a circle, pi r square, moving across the height h. So it makes a volume of pi r square h, right? Now, it gets slightly tricky when we are trying to calculate the volume of a cone. In cone, you can visualize a triangle rotating 360 degrees to form volume of a cone. The area of a triangle moving across 2 pi r at the bottom is making the volume of a cone. Now, in this case, the area of triangle, the base of the triangle is radius r, so r. Height of the triangle is height of the cone, h. So the area of triangle is half into h into r. H into r by 2. It's moving across the distance 2 pi r, which is the circumference of our circle at the bottom of the cone. So 2 pi r into RH by 2 becomes r square h. So ideally that should be the volume of cone, but it is not. Why? Remember, in area of a circle we said only one side of the radius is moving. Similarly, when we are making volume of a cone, when you are rotating the triangle, out of the 3 edges of the triangle, only one is moving. Only one edge out of the 3 is moving. So in this case, the volume that we get is 1 out of 3, 1/3. So it would be 1/3 r square h. That's the volume of a cone. Thank you for watching this full video. If this video helped you see math in a new light, then consider clicking on like, subscribe and share. It's a small act, but it goes a long way in helping us create more such content. Let's keep building this shared square of knowledge together, and I will see you in the next one. Thank you. Bye-bye.